the degeneration. So this is like a one-parameter family, one complex parameter family of some kind of variety. So maybe later we'll mainly look at the case of a Calabi-Yau variety. So you want to think of this, well, of course, this could be like a constant family, and then there's not so much to say. So somehow, but you want to study whatever this means, xt as t tends to 0. Right? So of course, this is not so clear what is meant by that. But let me just give one example of. So let's look at which will be in a Calabi-Yau. So let's say that xt is. So let me sit inside two-dimensional projective space. So let me do, so say x, y, z plus t, and then x cubed plus y cubed plus z cubed equal to 0 inside P2. Oops. So of course this, at least for t close to 0, this is a elliptic curve, or you can think of this as a geometrically, whatever that means, like a torus, but it's kind of a skinny torus, right? So because you see, if you plug in t equal to 0, something's going to happen. You can actually kind of change. I mean, essentially, the torus as a Riemann surface has kind of two parameters here, and you can kind of see that it looks like this. So as t tends to 0, this xt should somehow converge to a circle, like a real one-dimensional manifold. And somehow part of the objective is to try to, well, not to prove necessarily, but at least to make these kind of statements precise. So in what, I mean, I didn't say in what sense I want this convergence to happen, and that's exactly what I want to talk about. Okay. But just in order to be a little bit precise, I'm going to spend a lot of this first lecture not really talking about degeneration so much, but just kind of setting up formalism. So it'll be a little bit slow, and there'll be some overlap with a previous talk by Boesky. Okay. So I want to go back and just say what I mean by like algebraic projective varieties and complex manifolds. And so, I mean, not from the very beginning, but at least make some a little bit pedantic points, perhaps. Right. So, I mean, I'll get to Calabi-Yau in a while as well. But whatever I'm going to work with, I hope this is let's say smooth, complex, projective varieties. Right? So what I mean, extrinsically, by this I just mean that x has some subvariety inside some Pn of C. So this is just cut out by a bunch of homogeneous equations in n+1 complex variables. Okay, and then I assume it's smooth, which has a natural meaning. But I just want to emphasize this is just, there's nothing particular about C, so at this level I can just define it over any field. So this is just algebraically, and then if you want this more intrinsically, so then maybe I want, well, you can do this in different ways. So maybe think of XL. So this is, let's say, a polarized variety. I mean, smooth. Right? So X is well, a priori it will be projective as well, but a priori it's not, right? So this is some kind of algebraic variety. Over C, I mean, again, smooth, etc. And then I want L to be ample line bundle. this, then I get from I, this is just taking the global sections of L, embeds this into some projective, P. Maybe for N. Like this, or maybe a dual if you want to pick it up. Okay. So that's slightly more intrinsic. And here, when I talk about line bundles, I will think of line bundles sometimes as kind of geometric objects as fibering like a total space, or as an invertible sheaf. Okay, so I haven't done very much. And you get some more, when you study this in its generality, somehow the main hero here is the canonical bundle. So basically, so just sections, if I view this, so the sections of Kx are, well, holomorphic, or think of them as n-forms. Right? I mean, at this point, I haven't really defined what, there's no particular meaning of holomorphic n-forms. They're just kind of regular n-forms. Right? And where n is okay, and then of course you can go on. So there are kind of the three special cases which were already discussed in the last talk about some properties of this canonical bundle. So, oops. So we can have, so this Kx can be ample, or kind of anti-ample, or it could be trivial, or it could be something else. But those are at least three interesting cases. Right. So I'm going to have, so first is that Kx positive, so this means I mean that Kx is ample. So then you say that X is canonically polarized. This Kx, X comma Kx is a polarized variety in this case. And we have the opposite case. So this is like minus Kx is ample. And in general, I'm going to use for line bundles kind of additive notation. This is like Kx tensor like -1 or something, but let me not write like this. So this then X is, well, anti-canonically polarized, or just mono, the definition. Or then you have this Calabi-Yau case. And of course, so here I'm taking a somewhat, in some sense, both a restrictive and generous definition of Calabi-Yau. So I'm just going to say this is equal to 0, so just in the sense that it's linearly equivalent. Right? Linearly equivalent, so it has, so Kx has kind of a global non-vanishing section. It's not so important, but let me just, if I, for this purpose here, say that X is then Calabi. Yeah. Or sometimes, I mean, Calabi-Yau can be defined in different ways, and I think the reason for the name is not really from this definition, but from the Calabi-Yau theorem, which was already mentioned, and which I'll also come to. Right. And then sometimes you might want to exclude things like tori, and so you might require the variety to be simply connectors. So let me just do a couple of simple examples. Illustrate this. Nevertheless, do this. So let me take a hypersurface inside Pn, where d is the degree of just one homogeneous polynomial. Right? So then by adjunction, you can compute the canonical class of x. So it's the restriction of something on Pn to x. Right? Kx, if I just a bit careless here, this is just Kpn plus x restricted to x, and then you can figure out. So this implies that if d is less than or equal to n, then you have something that's x is Fano, and d is n plus 1, then x is Calabi-Yau. Canonically.